A compass looks simple. A small needle balanced on a tiny pivot, free to rotate. There's no battery, no electronics, and no sensing system. Physically, a compass is just a small magnet that's allowed to turn with very little friction. The reason it turns is that Earth itself produces a magnetic field. At every point on the planet, that field has both a strength and a direction. You can think of it as invisible arrows filling space, pointing roughly north-south, but slightly tilted depending on where you are. The compass needle is a magnet, which means it has a magnetic dipole moment. When a magnetic dipole sits in an external magnetic field, it experiences a torque. In plain language, the field tries to twist the magnet. If the needle is not aligned with the field, the torque rotates it. If the needle is already aligned, the torque is zero. Mathematically, that torque is written as tau equals m cross b. You don't need the vector math to get the idea. The important point is that the twisting effect is strongest when the needle is sideways to the field and disappears when the needle lines up with it. So the needle naturally rotates until it points along the magnetic field direction. Earth's magnetic field is tilted downward into the ground, except near the equator, but a typical compass needle can only rotate horizontally. Because of that, it mainly responds to the horizontal part of Earth's field. That horizontal component is what gives you a direction on a map. Near the magnetic poles, the horizontal component becomes very small, which is why compasses behave poorly there. You can also understand the alignment using energy. A magnetic dipole in a field has a potential energy equal to minus m dot b. That energy is lowest when the needle points along the field and higher when it's misaligned. The needle turns because systems tend to move toward lower energy. Once it reaches that minimum, it stops. In an ideal world, the needle would overshoot and oscillate forever. Real compasses don't do that because of damping. Friction at the pivot, air resistance, or liquid inside the compass slowly removes energy. That's why the needle settles smoothly instead of wobbling endlessly. One common source of confusion is what north means. A compass points toward magnetic north, not geographic north. Magnetic north is where Earth's magnetic field points downward into the planet. It doesn't line up exactly with the North Pole, and it moves over time. The angle between magnetic north and true north is called declination, and navigators correct for it using maps. Compasses can also be wrong if something nearby creates its own magnetic field. Steel, magnets, motors, or electric currents add a local field to Earth's field. The needle aligns with the total field, not just Earth's, which is why compasses misbehave near cars, buildings, or electronics. So in the end, there's no mystery. A compass works because Earth's magnetic field exerts a torque on a freely rotating magnet, causing it to align with the horizontal component of that field, while damping lets it settle into a stable direction.